Starting system operation. This video will summarize the operating principles and design variations of typical automotive starting systems. Starting systems have helped to make the modern automobile a reliable and convenient means of transportation. It provides an easy method of cranking the engine until it starts and runs on its own power. This video will explain the principles of basic DC motors before detailing the construction of high-power starting motors. It will also describe starter drive mechanisms, ignition switches, solenoids, and other components. The next video in this series will summarize the diagnosis and repair of starting systems. The theory presented in this video will give you the background needed to comprehend modern service and repair methods. To make a fundamental battery, place dissimilar metals in a beaker of acid. One metal rod would form the negative electrode and the other the positive electrode. A potential difference or voltage would be formed across the two electrodes. The result would be a very basic battery cell. In a car battery, the plates or electrodes are flat to increase surface area and electrical power. Separators are used to keep the plates from shorting or touching. If a load is placed across the cell, voltage will force electrons to flow through the load until the battery becomes discharged. Here we'll show you how a battery is constructed. By removing the cover, you can see the compartments in the battery case or housing that form the cells. Battery housings are made out of a synthetic plastic material designed to resist acid corrosion, temperature change, vibration, and other forces. Each compartment in the housing holds one of the battery cells. The positive plates, negative plates, and separators slide down into the cell compartments of the case. This cutaway shows how an actual battery cell is made. Note the plates are separated by insulating separators. The positive plates, the separators, and the negative plates are sandwiched together. Each battery cell produces roughly 2.1 volts. Since modern car batteries normally have 6 cells, the battery is called a 12-volt battery, but more accurately, it produces 12.6 volts, 2.1 volts times 6 cells. Note the battery symbol in this starting circuit diagram. It connects to the starter solenoid. A neutral safety switch is often used to keep the engine from cranking while the shift lever is in gear. The ignition switch feeds current to the starter solenoid when the driver turns the ignition key to start. When the ignition key is turned all the way, a small current flows through the solenoid windings, the ignition switch, and back through the battery. This energizes the solenoid and closes its contacts. A very high current can then flow through the starting motor, the solenoid and battery to crank the engine. A starting motor relies on strong magnetic fields for operation. A permanent magnet and a current-carrying wire both produce a magnetic flux or field. Since magnetic fields can attract and repel each other, they can be used to produce strong rotational forces inside an electric motor. A simple electric motor uses stationary field magnets that act against a rotating set of windings. A commutator and brushes feed current into the rotating windings. Current flows through the brushes, the motor windings, and back to the battery. The center frame is the foundation of an engine starting motor. It holds and supports the other major parts. The brush end frame connects to the rear of the center frame, and the drive end frame connects to the front or other end of the center frame. Field coils, or permanent magnets, mount inside the center frame to produce a stationary magnetic field. Armature bushings fit in the drive and brush end frames. They are used to support and allow the armature shaft to spin freely inside the starting motor assembly. The commutator mounts on one end of the armature shaft. The brushes rub on the commutator to produce a sliding electrical contact when the motor is running. Armature windings fit inside a metal armature core mounted on the armature shaft. This produces a very strong rotating magnetic field. A pinion gear is splined onto the shaft for engagement with the engine flywheel ring gear. A one-way clutch is constructed as part of the pinion gear to keep the flywheel ring gear from spinning and damaging the motor when the engine fires and runs on its own power. A lever arm is used to push the pinion gear outward whenever the starting motor is energized. A plunger, and sometimes a pole shoe, is used to act upon the lever arm. Some starters use a solenoid to physically move the plunger, lever arm, and pinion gear back and forth. This close-up shows the commutator segments. Each segment is connected to an armature winding. Insulating material is undercut and separates the commutator segments. This allows the brushes to feed current into each set of armature windings individually. On the other end of the armature shaft, note that a groove is machined for a snap ring. Spiral splines on the shaft are used to make the pinion gear and clutch turn with the shaft, but they allow the gear to slide back and forth. Some starters have a thick C-clip type snap ring like this one to secure the pinion gear assembly. A cup type washer fits over the C-clip to protect it. This starter cutaway shows how the commutator end of the armature shaft mounts in bushings in the end frame. A thrust washer often fits between the armature and the brush end frame. The soft metal bushing press fits into the end frame. Grease reduces friction between the bushings and the armature shaft. This cutaway of the drive end frame shows the shaft bushings, thrust washer, and C-clip washer in chrome. The flywheel ring gear and transmission torque converter are rotating behind the starter. Starter bushings are usually made of a soft brass-bronze alloy to reduce shaft wear. The bushings can be removed and replaced in their housing during a rebuild. This cutaway shows field coils mounted in the center frame. They produce a strong magnetic field which repels and attracts the magnetic fields produced around the armature. Note the large wires that feed current into the starter brushes. Approximately 100 amps can be fed into the starter when energized. This high current produces a strong magnetic field which is powerful enough to spin the engine crankshaft. In the past, most starting motors used heavy gauge field coils mounted around iron pole shoes. The magnet and windings produced a stationary field. Now the trend is to use high-power permanent magnets only, without the field windings. This reduces motor size, weight, cost, and complexity. Mentioned briefly, the three major housings of the starter are the brush end frame, shown here, the center frame, and the drive end frame. Long bolts feed through the brush end frame, center frame, and thread into the drive end frame to hold the starting motor together. By removing these two bolts, you can disassemble the starter. Large holes in the thick drive end frame are provided for bolting the starting motor to the engine. An opening is provided so that the pinion gear can engage the flywheel ring gear. Here you see a starting motor attached to the side of the engine. The starter normally bolts to the engine block or to the clutch housing. A strong mounting of the starting motor is needed to keep the pinion gear and ring gear meshing quietly. This exploded view shows a gear reduction type starting motor. With this design, a small gear on the armature drives an idler gear. The idler gear drives a larger output gear. Since the output gear is larger than the gear on the armature, a gear reduction is produced. The armature will spin at a higher RPM, while the pinion gear turns more slowly, but with much higher torque. Note that the output gear is formed as part of the clutch and pinion gear assembly with most designs. The starter drive refers to the pinion gear clutch and related components used to engage the pinion gear with the flywheel ring gear. The pinion gear clutch allows the pinion gear to turn in one direction, but locks the gear in the other direction. Rollers are used inside the one-way clutch. Rollers allow freewheeling when the clutch is rotated one way, but the rollers wedge out and lock the clutch internal surfaces when turned in the other direction. The pinion gear must also be splined to its shaft so that it is free to slide outward and into engagement. As you will learn in the next video, the starter clutch assembly and pinion are the most common parts to fail in service because of the severe loading. Splines inside the pinion assembly mesh with the splines machined onto the armature shaft. The spiral splines help throw the pinion gear outward when the starting motor is energized. The teeth on the pinion gear slide into and mesh with the teeth on the ring gear bolted to the engine crankshaft. Since the ring gear has a large number of teeth and the starter gear has only a few teeth, the motor has enough torque to crank the engine until it starts and runs on its own power. When the engine starts, the driver releases the ignition key so that the pinion gear can retract away from the spinning flywheel ring gear. The one-way clutch keeps the ring gear from turning the motor armature and causing starting motor damage. Here is a starting motor design that uses a movable pole shoe to move the pinion gear into engagement. By removing a sheet metal cover, the movable pole shoe can be studied. When the motor is energized, the resulting magnetic field pulls down on the pole shoe. A lever on the other end of the movable pole shoe pushes the pinion gear outward and into the ring gear. This animation shows the basic purpose of a starter solenoid. When the key is turned to start, a small current flows through the solenoid windings and ignition switch. This pulls up on the plunger and closes the solenoid contacts. Hundreds of amps can then flow through the solenoid to the starting motor. Here you see an actual solenoid mounted in the engine compartment. The large battery cable and starter cable bolt to the solenoid. The smaller wire goes to the ignition switch. The small current flow into the solenoid produces a magnetic field around the solenoid windings. This field is used to attract and pull the plunger into the windings. When the plunger and disc are pulled up, the contact disc touches both the large lugs formed as part of the battery cable and starter cable studs. Battery current can then flow directly to the starting motor. This cutaway shows a starter solenoid mounted on the side of the starter. Besides closing the battery to starter circuit, it also moves the pinion gear into engagement with the ring gear. The motion of the solenoid plunger is used to perform two functions. This solenoid cutaway shows the large contact disc in chrome and the large battery and starter cable lugs in chrome. The cutaway also shows the fine windings used to produce the strong magnetic field in the solenoid, which acts on the large iron plunger. A spring is used to push the plunger back into the retracted position. Here you can see how the contact disc is moved by the solenoid windings to close the battery to starter circuit. When mounted on the starter, remember that solenoid is used to move the pinion gear into engagement and also to energize the motor at the same time. There are two basic types of ignition switches, the older in-dash switch and the more modern in-column mounted ignition switch. Besides powering the starter solenoid, the ignition switch often feeds current to other circuits. The terminals are often labeled for easy troubleshooting. The key tumbler fits into the front of the in-dash switch. It rotates the switch into its start, run, off, and accessory positions. When in the start position, current is often fed directly to the starter and then to the ignition coil. When released to run, current flow to the starter is interrupted, but current is still fed to the ignition coil so the engine will operate. Here you can see a steering column mounted ignition switch. It bolts to the outside of the column under the dash. The ignition key tumbler and rack and pinion gear mechanism transfer motion down to the ignition switch. A long metal rod links the switch with the rack and pinion gear mechanism. This animation demonstrates the action of a starting circuit while cranking and then after engine starting. First, low current flows through the ignition switch to energize the solenoid. The solenoid closes and high current flows to the starting motor. The engine cranks until the driver releases the ignition key. Current is fed directly from the solenoid to the ignition coil. When the key is released and the engine fires, the alternator feeds current to recharge the battery and also to provide current for the other electrical devices on the car. On older vehicles, current is sometimes fed through a resistor to the ignition coil. Since the starter draws enough current to lower battery voltage, the ignition coil is designed to operate on about 10 volts. Automatic transmission or transaxle-equipped cars use a neutral safety switch. It prevents the engine from cranking unless the shift lever is in park or in neutral. This is a safety feature that prevents the engine from starting in reverse or the other drive positions. Only when in neutral and park does the neutral safety switch complete the circuit from the ignition switch to the starting motor. It would be very dangerous if the engine were able to crank with the shift lever in drive or in reverse. With a manual transmission, a clutch switch is sometimes used. It is another safety device that only allows engine cranking when the clutch pedal is pressed to the floor. Again, this prevents the engine from